So I'm recording the lesson for the people that are on Kairos so that they can watch at their leisure. I would ask that you stop talking though, please. Thank you. So we're starting the last unit for this year. So that's going to be chapters 20 and 21. These two chapters are on ideas involving calculus, which I'm pretty certain nobody in here has seen yet before. So unlike a lot of the things that we've done this semester that have been largely like, oh yeah, I kind of remember doing this before, they've been a little reviewish. This one probably will not be for any of us. So just as a little historical background, calculus is a rather recent development in the branches of mathematics. So calculus was developed independently by two separate men in the 1600s or 17s, late 1600s, early 1700s. So Isaac Newton was one of them, and Gottfried Leibniz is the other. And Newton is the one that kind of gets more attention maybe in the West. And his development of this mathematical technique was kind of an afterthought. It was like the appendix to a paper that he wrote kind of describing gravity, which is probably what most of us, when we hear Isaac Newton, is the first thing we kind of think of. So he developed these mathematical techniques so that he could better describe and study gravity. And specifically, the question he was asking was, how fast is a falling object moving at a given instant? So, you can calculate the average speed that something went when it fell by just timing how long it takes to fall that distance, and then taking the distance and dividing by time, and that's going to be your average speed that object fell at, right? But if I walk up to the top of a ladder and I drop, a rock, and I want to know how fast is it moving, 2 meters into the fall, they didn't really have a way to describe that, or even to calculate that, or even predict how fast that object was going to be moving. And this was the question that kind of Newton wanted to answer. So the mathematical tool that he created in order to do that is called the derivative. And in calculus, there's kind of two big branches of calculus. There's integral calculus and there's derivative calculus. In this course, we're only going to be talking about derivative calculus and really just kind of dipping our toe into the pool of derivative calculus, so it's not going to be a very expansive trip, but it'll be enough to where we can do a little bit with it. So the derivative is like a function, I should say, it's an operation on a function. So we do an operation on a function. Now this is new, right? Anytime that we've, in our mathematics course work to this point, we've used an operation on a number or a vector or an angle, or some kind of mathematical object that wasn't as abstract as a function. That operation outputs another function, which we call the derivative. that describes the slope of the original function in terms of x. So this is kind of what this is doing. So this derivative is an operation. So, for example, the derivative of f of x equals x squared is, so one notation we use to describe a derivative is the prime mark here, and that derivative we'd say f prime of x is equal to 2x. Now, we haven't talked about how to do this yet, or really what this means at all. I'm just talking a little bit about the mechanics of what the derivative operation is doing, right? So we're starting with one function, and after we take the derivative of it, or find its derivative, the result is another function. Okay? Everybody's okay with that? So we input a function, we output a new function. Kind of like composition. You guys kind of remember that from Algebra 3-4. So this derivative function here, if I say plug 1 in for x, says then the slope of f of x at x equals 1 is 2. That's kind of how you can use the derivative. So the derivative is sometimes called a slope function, because what it's doing is it's outputting slopes for the original function. So if I wanted the slope at x equals 5, I'd plug 5 in for x into the derivative and output. What would output is the slope. Does that make sense to you guys in terms of like what this derivative is giving us? Okay. The thing you should be thinking, though, that seems a little fishy is like, well, wait a second here, Mr. Gulick. How can a single point have a slope? That seems a little bit fishy. And this is exactly the issue that Newton was having when talking about calculating the speed of a falling object at an instant. Right? It was easy to calculate the average speed. If I have like the starting and the ending, I can just time how long it takes to get from the beginning to the end and take that distance and divide it by the time. That's essentially what he's doing, is taking a slope. So the idea geometrically, if we have some curve and we say we want to find the slope of this point here, what he did was he said, okay, well, I can take the slope of these 2 points, and then I can take the slope of these 2 points, and then the slope of these 2 points, and eventually I just keep moving them closer and closer and closer and closer, sandwiching down to that single point, and I can observe kind of the pattern that's happening there, and in the end I end up with what is the slope at that singleton point. Because what's the problem if I try to apply the slope formula with just 1 point? So like, let's say this is the point 1, 2. If I try to do the slope formula just 1 point, we end up with something undefined, right? So the whole idea of this derivative is to get around this notion of, oh, if I have try to do something instantaneously involving like the slope of one point, I can't do that with the slope formula because I end up with an undefined operation or an undefined value. So I've created this new approach of kind of taking a point on either side, finding the slopes of these things, and kind of progressing down until I end up with the slope at just that one specific point, max.
Like, won't there always be two like points you can put like in between before you reach the actual?
So you're kind of doing this infinitely many times.
Okay, so you don't actually do it forever. It's just like
Right. So what I'm talking about is a way to like approximate this value. There is a mathematical kind of operation that you can do that like looks at like infinitely many times of doing this, called a limit, that if you take a college calculus course, that's kind of where they would start. In terms of this class, that is not part of the required curriculum, so I'm just going to kind of skip around doing that, or skip over doing that. But yeah, your math detector should say, seems like there's a little bit more going on here than what you're letting on, and there is a lot more detail that we're kind of glazing over. But that is the idea. Does that make sense? Okay. So let's talk a little bit about, we have some little idea of kind of what a derivative is and the information the derivative is giving us. Let's talk about notation here. And this can be a little bit of a bear because since calculus kind of has two different founders that kind of both develop these ideas independently of one another, unfortunately we have like a bunch of different notations because of that. So we can say the derivative of, let's say, f of x equals yada yada yada, can be written as f prime of yada 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 So if we have the derivative of y equals yada yada yada, we can write it as y prime equals, and then whatever that is. Or a third way is if we have y equals yada yada yada, we can write the derivative as dy dx equals yada yada yada. And you might say, like, why dy dx? That seems weird. Well, remember that derivatives are about slopes. And we said the slope formula back in middle school is y2 minus y1 over x2 minus x1. You might have also seen that written as like delta x over delta y. In mathematics and physics, oftentimes we use the capital Greek letter delta to represent change in. The lowercase Greek letter delta looks like this, where this would be like, we use the lowercase Greek letter delta for like an instantaneous change in, and then as we English language this up, we've just turned those lowercase Greek letter deltas into these. So again, it should when you see this, it should remind you of the slope formula, which is kind of the idea here. So those are the kind of the notations. So if you see like f of prime equals or y prime equals, those are indications that what you're talking about is a derivative. Or if you see dy dx, that is something you should see as like one whole object, like the dy dx. Don't think about it as a fraction, just think about it as a single thing, like one symbol. And that's another way to represent a derivative. The process of taking the derivative is called differentiation. So, different ways we could ask you, we could say find the derivative of this. We could say differentiate this. You know, like find the derivative of f of x, or take or differentiate f of x. Either of these operations, or either of those directions kind of represent the same thing. So let's talk about how to do this. So there's lots of different rules and techniques we can use for differentiation. There is only one rule for this course that's required that we need to talk about. That one rule is called the product rule. And it says that if f of x equals a times x to the n, then the derivative is a times n times x to the n minus 1. So let's look what we're doing. Is we're taking whatever the exponent was, multiplying it to the coefficient, and then subtracting 1 out of the exponent. So let's do a bunch of examples here to kind of get our feet wet with doing something like this. Sound good to you guys? And this is the skill that you're really going to need to kind of have, okay? So if I want to differentiate f of x equals 3x squared, I would write f prime equals, and then using my product rule from above, I'm going to take 2 and multiply it to 3, and then my exponent I'm going to subtract 1. So I write f prime equals 6x. And that's it. You're done. The derivative has been completed. The differentiation is over. Let's do this a second. Let's do another example. Yes? Okay. And that's really what I have planned for the next, 10 or 15 minutes here. We're just going to run through a bunch of the different examples here because there are some tricky things that can come up. Let's write this as y this time. So if I want to take the derivative of this, what I'm going to do is I'm going to do that product rule distributively. So I'm going to do the product rule for each of these 4 pieces. So this is rare, right? In mathematics, we don't see a lot of times where an operation distributes. Until this point, really the only other operation that we saw that was distributive was multiplication and division. But the derivative operation does distribute, which is very, very nice. It makes life much, much easier. So I might write y prime equals. And then what's going to be the derivative of this first piece? Or we could just write 21x squared, right? And you don't necessarily need to show that intermediate step, but since these are notes, I'm going to write them down so when you go back and look at them, that's there. Okay, what's the derivative of this next piece going to be? 4x, 2 times 2, times x to the 2 minus 1. Getting a little trickier now. What is this next, the derivative of 7x going to be? Good. 7 times 1 to the x minus 1, which would just turn into 7. And then, also tricky, what's the derivative of 2 going to be? Well, we can write 2 as 2 times 1, right? And we know that anything to the 0 power is the same as 1, right? So if I think about this as 2x to the 0, I would have 2 times 0 times x to the 0 minus 1. Well, what does that all turn into? Just 0, right? So my observation here is the derivative of a constant is 0. So if you're taking the derivative of any constant, like the derivative of 15, or the derivative of 107, or the derivative of pi, all of those are 0. Which hopefully makes sense, right? Because if I think about this as the slope, if I have, say, the line y equals 2, what's the slope of this line? 0 everywhere, right? So its derivative should be 0, because the slope of that line is 0 everywhere. Everybody okay with that? So we would write our final answer then here as 21x squared plus 4x plus 7. Okay, let's do So this one is more tricky yet. We see two things that probably look a little unfamiliar. We see a radical, and then we see x's in the denominator. We haven't seen any of those in our examples yet. In order to take the derivative of this, though, what we need to do is we need to get it to look like something in this form here. So in order for us to use our product rule, product rule, why did I write that? This is the power rule. Goodness gracious, Mr. Hulick. I need to get the pieces here to look like the power rule. So how can I rewrite 3 over x squared as a times x to the n? Well, I remember that if I have an x in the denominator, I can rewrite it as an x in the numerator with a what kind of exponent? Negative exponent, right? So I can just turn that into 3x to the negative 2. And I remember that radicals are the same things as, or I can also write them as exponentials, right? What exponent is the same as a square root? A 1/2, right? So I will take an intermediate step to rewrite these so that they are in kind of that same form so that I can use my power rule. And now I have enough, or now I have it in a form where I can apply my power rule. So what will the derivative of this first piece be? Very good. So I did negative 2 times 3 to give me the negative 6. And then I subtracted 1 from the negative 2 to give me the negative 3. Are we okay with that? Okay. What will the derivative of this 7x to 1/2 be? Very good. So again, I did 1/2 times 7 to give me the 7 over 2. And did 1/2 minus 1 to get me the negative 1/2. And the derivative of negative 3 is 0. So this we could write as, keep as our final answer, or if you wanted to, you could write it like this way. That's okay too. God bless you. You're welcome. And at this point, guess what, guys? You know everything you need to know about taking derivatives for IB Math Studies. So, just to recap here, what does the derivative tell you about? It tells you about the slope of the function, or the original function, right? It's going to tell you about the slope of the original function. How do we take the derivative? We make sure that our function is in terms that look like this, and then we apply the power rule to do that. And we just go piece by piece. Differentiation is distributive, so we can just do it one piece at a time.